This is a video for MEI Core Pure Mathematics, second order differential equations 1, homogeneous equations, 1.3, finding particular solutions given initial conditions. In a previous video we have seen that the general solution of this differential equation is y is equal to a e to the 3x plus b e to the minus 5x. So if we could find the values of a and b that were needed, that would give a particular solution to this differential equation. And to do that, we need two extra pieces of information. So two arbitrary constants, two extra pieces of information. You could think of this a bit like simultaneous equations. If we've got two simultaneous equations with two unknowns, we've got enough information to solve them. If we have three unknowns, we need three equations, and so on. Sometimes when we're finding a particular solution, we're given initial conditions. And this is when the information is given for the same value of the independent variable, often x equals 0. So for example, we might have that y equals 0 when x equals 0, and dy by dx equals 2 when x equals 0. So we've been given two pieces of information, both related to when x equals 0. It's called an initial value problem. So in this example, we want to find the particular solution for this differential equation for these initial conditions. Well, we already know the general solution to this. We know that the general solution is y equals a e to the 3x plus b e to the minus 5x. If I differentiate this, I'm going to get that dy by dx is equal to 3a e to the 3x minus 5b e to the minus 5x. And so starting out, I can put in that y equals 0 when x equals 0, and that's going to give me that a plus b is equal to 0. The second piece of information is that dy by dx is equal to 2 when x equals 0. And so that's going to give me that 2 is equal to 3a minus 5b. So I've got two simultaneous equations in a and b. A plus b equals 0. 3a minus 5b equals 2. So if I multiply that by 5 and add them together, I'm going to get that 8a is equal to 2, which means that a is equal to a quarter. And from here I can see that a is equal to minus b, so that's going to give me that b is equal to minus a quarter. And so the particular solution for those initial conditions is going to be y is equal to 1/4 e to the 3x minus 1/4 e to the minus 5x. There is that working written up a little bit more neatly for you. So there we've taken the general solution, differentiated it so that we get an expression for dy by dx. We've used the first set of initial conditions to give me an equation for a and b, and the second set of initial conditions to give me an equation for a and b again, and then solved those two equations simultaneously to give me the values of a and b, and hence the particular solution. So here's a plot of that solution curve for those values of a and b, and you'll see that it does indeed go through the origin, so y is equal to 0 when x equals 0. And if you look at this blue line, which is the gradient at x equals 0, you've got a height 2 here for an x value of 1, so you have got a gradient of 2. So that agrees with that as well. And so we need two pieces of information, which is what we've got here, to be able to sort out a particular solution for a general solution with two constants in. The next video in this sequence is 1.4, finding particular solutions for boundary conditions.